Imagine a world where your thoughts are your ultimate password. Brainwave Biometrics, leveraging the unique electrical activity of your brain, is transforming this concept into a tangible reality. This cutting-edge technology promises a new era of security, offering an authentication method as unique as your own mind. Biometric authentication using brainwaves is an emerging field that harnesses the distinct patterns of your brain's electrical activity. Typically measured by electroencephalography, EEG, these patterns provide a highly personal and robust identifier. This innovative approach merges neuroscience with cybersecurity, creating a formidable new layer of digital protection. At its core, neuroauthentication relies on the principle that every individual's brain generates unique electrical signals. These signals, influenced by genetics, brain structure, and cognitive processes, form a brainprint. Unlike traditional biometrics, this brainprint is dynamic yet consistently unique to you. The process begins with the capture of your brain's electrical activity. This is primarily achieved using electroencephalography, EEG devices. These devices consist of electrodes placed on the scalp, which detect the tiny voltage fluctuations produced by neuronal firing. Once recorded, these raw brainwave signals undergo sophisticated processing. Algorithms analyze the unique patterns, frequencies, and amplitudes present in your EEG data. This intricate analysis allows the system to create a digital signature, or brainprint, that can be used for identity verification. Brainwave authentication fundamentally relies on brain-computer interface, BCI technology. BCIs establish a direct communication pathway between the brain and an external device. In this context, the BCI interprets neural activity to facilitate authentication. BCIs can be broadly categorized into invasive and non-invasive types. For authentication purposes, non-invasive EEG-based BCIs are predominantly used. These systems capture brain signals without requiring surgical implantation, making them practical and user-friendly for widespread adoption. The BCI acts as the bridge, translating complex brain signals into actionable data. It processes the raw EEG, filters out noise, and extracts relevant features. This processed data is then fed into machine learning models for pattern recognition and identity verification. Brain activity is characterized by different frequency bands, each associated with distinct mental states. These include delta, 0–5 to 4 Hz, deep sleep; theta, 4 to 8 Hz, drowsiness, meditation; alpha, 8 to 12 Hz, relaxed, awake state; beta, 12 to 30 Hz, active thinking, alertness; and gamma, 3100 plus Gs, intense concentration, problem solving. Each person's unique blend and response across these frequencies contribute to their distinct brainprint. For authentication, algorithms often analyze how these frequencies change in response to specific stimuli or tasks. For instance, a user might be asked to imagine a specific action or focus on a particular image. The resulting brainwave patterns across these frequency bands are then used for verification. Early research on EEG-based authentication was confined to controlled laboratory environments. However, significant advancements in sensor technology and signal processing have propelled this technology into real-world applications. Commercial EEG headsets, once bulky and expensive, are now more affordable and user-friendly. These consumer-grade devices, while not as precise as clinical EEG equipment, have proven sufficient for capturing distinct brainwave patterns. Studies have successfully validated EEG-based authentication outside of laboratory settings. This demonstrates the technology's potential for practical deployment in everyday scenarios. The efficacy of any biometric system is measured by its accuracy metrics. For brainwave authentication, studies have consistently achieved high accuracy rates. These rates often exceed 90%, indicating a strong capability to correctly identify legitimate users while rejecting imposters. Key metrics include the false acceptance rate, FAR, and the false rejection rate, FRR. FAR represents the percentage of unauthorized users incorrectly granted access, type 1 error. FRR indicates the percentage of authorized users incorrectly denied access, type 2 error. Minimizing both is crucial for a robust system. For example, One notable study achieved an authentication accuracy of 92.6%. This impressive result was coupled with a low FAR of 2.5% and an FRR of 5.0% for performed motor tasks. Such figures highlight the promising reliability of brainwave biometrics, even under specific cognitive loads. Many brainwave authentication systems leverage evoked potentials or responses to specific cognitive tasks. Asking a user to think about a particular memory, perform mental arithmetic, or visualize an action generates unique and reproducible brainwave patterns. This active engagement enhances the distinctiveness of the brainprint. This task-based approach adds another layer of security. It makes it significantly harder for an imposter to replicate the required brain activity. The combination of inherent brain uniqueness and task-specific neural responses creates a highly robust authentication challenge. Brainwave authentication offers several compelling advantages over traditional and other biometric methods. Its inherent nature provides a level of security and convenience that is difficult to match. These benefits position it as a strong contender for future authentication paradigms. Firstly, brainwaves are always present and continuously generated by a living brain. Unlike passwords, which can be forgotten or stolen, or physical biometrics like fingerprints, which can be lifted or replicated, brain activity is internal and dynamic. This constant presence ensures a continuous and seamless authentication experience. Secondly, the very nature of thought makes it inherently private and unobservable. You cannot force someone to think a specific thought, nor can you directly observe their internal cognitive processes. This makes brainwave patterns incredibly difficult to spoof or compromise, offering a superior level of privacy and security. Furthermore, brainwave authentication can provide an inclusive solution for individuals who cannot use other biometric methods. People with physical disabilities, injuries affecting fingerprints or retina, or those with certain medical conditions might find traditional biometrics challenging. Brainwave authentication offers an alternative, accessible pathway to secure access. The development of robust brainwave authentication systems relies on advanced signal processing and machine learning techniques. These technologies transform raw EEG data into reliable authentication credentials. Understanding these methods is key to appreciating the sophistication of this field. As mentioned, most current work relies on electroencephalography, EEG, to capture brainwave data. EEG is a non-invasive neurophysiological measurement technique that records the electrical activity of the brain. It detects voltage fluctuations resulting from ionic current flows within the neurons of the brain. The electrodes placed on the scalp measure these tiny electrical potentials. The resulting EEG signals are then amplified and digitized for analysis. The quality of the EEG recording is paramount, as noise and artifacts can significantly impact authentication accuracy. To effectively learn from the time series nature of EEG recordings, researchers frequently employ long short-term memory, LSTM networks. LSTMs are a specialized type of recurrent neural network, RNN, particularly adept at processing sequences of data. They can learn long-term dependencies, making them ideal for analyzing the temporal patterns in brainwave signals. Unlike traditional neural networks, all STMs have internal memory cells that allow them to retain information over extended periods. This capability is crucial for decoding the complex, evolving patterns of brain activity. LSTMs can identify subtle, unique temporal features in an individual's EEG, which are then used for authentication. To further enhance the performance and robustness of brainwave authentication systems, machine learning ensembles are often utilized. Bootstrap aggregating, commonly known as bagging, is a powerful ensemble technique. It involves training multiple models, for example, several LSTM networks, on different subsets of the training data. Each subset is created by sampling with replacement from the original dataset. The predictions from these individual models are then combined, typically through averaging or voting, to produce a final, more accurate prediction. Combining LSTM networks with bagging significantly improves authentication performance by reducing variance and preventing overfitting. This ensemble approach leads to more reliable and generalizable brainprint recognition. The potential applications of brainwave authentication span various sectors, from cybersecurity to personal device access. Its unique properties make it suitable for scenarios demanding high security and user convenience. As the technology matures, its integration into daily life will become more widespread. One of the most critical use cases for brainwave authentication is securing authorized access to sensitive data. This includes confidential corporate information, personal health records, financial accounts, and government databases. The inherent difficulty in spoofing brainwave patterns provides a robust defense against unauthorized access. Imagine accessing your cloud storage or a secure network simply by thinking a specific thought. This eliminates the vulnerabilities associated with passwords, such as phishing or brute force attacks. Brainwave biometrics could become a cornerstone of future enterprise security architectures, offering unparalleled data protection. Experiments have already demonstrated the feasibility of EEG-based mobile phone authentication. Users could unlock their smartphones or authorize transactions by simply wearing a compact EEG headset or even through integrated sensors in future devices. This offers a seamless and highly secure alternative to PINs, patterns, or even fingerprint scans. The convenience of hands-free authentication on mobile devices is a significant draw. It could revolutionize how we interact with our personal technology, making security an intuitive and effortless part of the user experience. This integration would also pave the way for more personalized and context-aware mobile interactions. Brain-computer interfaces, BCIs, the underlying technology for brainwave authentication, are becoming increasingly popular in both medical and non-medical fields. In medicine, BCIs are transforming lives by enabling communication for paralyzed patients or controlling prosthetic limbs. They offer a new means of interaction for individuals with severe motor impairments. In non-medical fields, beyond authentication, BCIs are exploring applications in gaming, virtual reality, and cognitive enhancement. Imagine controlling a drone with your thoughts or navigating a virtual world purely through neural commands. The ability to communicate directly between humans and machines based on neural activity opens up a vast array of possibilities for innovation and human-computer interaction. Despite its immense promise, brainwave authentication faces several challenges that need to be addressed for widespread adoption. These include technical hurdles, practical limitations, and ethical considerations. Overcoming these will be crucial for the technology to reach its full potential. A primary challenge lies in achieving high accuracy and reliability in non-laboratory environments. Real-world conditions introduce significant noise and variability into EEG signals. Factors like head movement, muscle artifacts, for example, blinking, clenching jaw, environmental electrical interference, and even emotional states can distort brainwave readings. Developing robust algorithms that can effectively filter out this noise and maintain consistent performance across diverse user conditions is essential. This requires extensive data collection under varied real-world scenarios to train and validate the authentication models. Miniaturization and improved signal quality of consumer-grade EEG devices are also critical for practical deployment. More studies are needed on subjects who are not mentally healthy to improve the collectability, stability, performance, and acceptability of brain biometrics. Neurological conditions, mental health disorders, or even temporary states like stress or fatigue can alter brainwave patterns. This variability could potentially impact the accuracy and reliability of authentication for certain individuals. Understanding how these factors influence brainprints is vital for developing inclusive and robust systems. Research must explore adaptive algorithms that can account for individual differences and transient cognitive states. Ensuring the system remains reliable across a broad spectrum of users, regardless of their mental state, is a significant area of ongoing research. The use of brainwave data for authentication raises profound ethical and privacy concerns. What happens if brainwave data is compromised? Could it reveal sensitive information about a person's cognitive state, intentions, or even medical conditions? The potential for brain hacking or unauthorized access to neural information is a serious consideration. Establishing clear regulatory frameworks and robust security protocols for handling brainwave data is paramount. Users must have full control over their neural data, with transparent consent mechanisms and strong encryption. Addressing these ethical dimensions proactively will be crucial for public trust and acceptance of brainwave biometrics.